This is 40.c. This is properties of inverse functions. Now, I want to talk about just first of all what an inverse function is. If you remember what we did with inverse functions, we said, for instance, y equals, and it had a value, and then you solved for x and exchanged the x and y to say this is an inverse function of another function. In other words, the input gives you an output, but if I put the output into the input, I get the opposite. And I know that sounds confusing. If you need to go back and look at inverse functions as a refresher before this lesson, that may be beneficial to you. So the very first thing we're going to talk about is the properties of inverse functions. And the properties of this would be, first of all, f composition g and g composition f are not the same thing. Remember that f composition g means put the second term g into the f term. And the g composition f means put the f term into the g term, or the g function. So we're going to talk about this first of all. This is not part of your book. It doesn't have an inverse function like this. But this is a refresher here about what they're talking about. That if I put f composition g is different than g composition f. So I went ahead and said f of x equals x squared plus 1. And the g of x equals x squared. If this works out right, what we're going to do is we're going to figure out that these two are not the same. So I'm going to say f composition g of 2, and I picked 2 just so we have a real number that we can compare. Although that should be x, it could be any number that I put in there. It should always work out. So when I look at this, I say the second one into the first one. So I want to put an x squared in for the x on this one. So I put the x squared in for the x, it was already squared, plus 1. X squared is x to the fourth, plus 1. Okay, if I then went ahead and put in my 2 in here, 2 times 2 is 4, times 2 again is 8, times 2 is 16, and then I say plus 1, that's 17. Well, if f composition g was the same as g composition f, I should be able to put the f into the g right here on this one for g composition f of 2 and get the same number. When I do so, I say x squared plus 1 squared. Okay, now what did I do? I put the x squared plus 1 function in for the x in here. I pretended that's a container, and I put this, and x squared plus 1 is substituted it inside. And then when I did so, I went ahead and said, well, that's squared, so I have to FOIL x squared plus 1, x squared plus 1. When I do so, I'll say x squared times x squared is x to the fourth. X squared times 1 is x squared. 1 times x squared is x squared. And 1 times 1 is 1. Combine my like terms and I'll get x squared, or x to the fourth plus 2x squared plus 1. At this point, I'm going to go ahead and plug in each one of these values of 2. 2 to the fourth is still 16. 2 squared is 4 times 2 is 8. And then I say plus the 1. So that carries on, and that gives me 25. Notice that these two numbers are not the same. If they were the same, it proves the functions are inverses of each other. Now, let's look at the example, another example here, and say, what if I had two different functions, and we'll see if these two, f composition g is the same as g composition f. Now, I chose to use just x in here just so you could see it, although we could put any value in for x1. This could be 2, this could be 5, this could be 343. It wouldn't make a difference if if f composition g equals g composition f, the two functions are inverses of each other. Now, I saved you the steps of saying y equals 2x plus 1, and then solving for x and dividing it all out and switching x and y and getting this. I already know these are inverse functions because I set them up that way. But we're going to go ahead and plug one into the other and see how it works. F composition g of x equals 2, right? I'm going to plug in the second one, 1/2 x minus 1/2, into this x here. When I do so, I say 2 times the second one, right? Plus 1, because x was up here. I shoved it up into there. I substituted it in for the x using the parentheses. Well, 2 times 1/2 is 1x. 2 times a negative 1/2 is 2 over 2, which is 1. So I have a negative 1. And then I said plus 1. So negative 1 plus 1, that equaled x. Well, that's interesting. So that means that when I plugged the second one into the first one, I'd ended up with x. If I would have had a 2 in here, I would have just, x for like I did up here, this would have just been a 2. Now I come down here on the G composition f of x, and I do the same thing, except now I'm taking the first one, the f of x, and substituting in. So 2x plus 1 gets shoved down into this x right here, right? So now I have 1/2 of 2x plus 1 minus 1/2. I go ahead and distribute this out. 1/2 times 2, well, that made it easy. 1/2 times 1, 1/2, minus 1/2 equaled x. These two are inverses of each other because the f composition G equals G composition f. And if that's true, they are inverse functions. Look at, and this is the way the book's writing it, the f of g of x equals x, and the g of f of x equals x. And that would be f composition G equals G composition f. Don't let the different way they've written this be confusing to you this time around. The book has always used the f composition G and G composition f, but really what that's saying is I'm putting the g of x in for the f, or I'm putting the f of x in for the g. It means the same thing, just don't let that nomenclature, that way of writing it, confuse you. 40.5, this is the example, says the f of x equals 1/3 of x minus 3, and the g of x equals 3x plus 9. Now, if I worked this problem out and I said y equals 3x plus 9, and I said find the inverse function of this, I would move the 3x over to, or the 9 over to the other side and get y minus 9 equals 3x. I divide everything by 3 and get 1/3 of y minus 9 over 3 equals x. Okay, and then I would rewrite this as y equals 1/3 of y minus 3. And if you'll notice, that is what they have. These are inverses. We're starting out with those being inverses. But we're going to look at this and say, how could I prove these are inverses of each other without having to solve one and the other? So I'm going to know that the inverse functions are the f composition G will equal the G composition f. So the first thing I do is f composition G of x, which means I'm going to take that 1/3, and instead of x, I'm going to plug in the 3x plus 9. I'm substituting that in, minus the 3 right there. So then notice this is this whole equation down here, except for x, I'm putting in the g of x. When I do so, I say 1/3 times 3 is 3/3. 1/3 times 9 is 9 over 3. And then minus my 3. 3 over 3 is 1. That's 1x. Plus 3 minus 3 is x. Well, that worked out well. That one does work. So we do the G composition f of x, and that works out the same way and gives me x again. Now, if either one of these did not work out for x, then it is not an inverse function. So all we're doing here is we're using inverse functions to prove, or using G composition f and f composition G, both equaling the same value to prove that they are inverse functions of each other. Don't let all this extra terminology get confusing to you. This is not a difficult step for you to handle. If as long as you remember what f composition G and G composition f are and how to work with them, you'll realize that if I find out that the f composition G of a number is the same as the G composition f of a number, then the two functions are inverses of each other. And this is how you prove it.